Okay, in this video we'll be going over the array object. In MFM, the array object captures an antenna array, so an array of antenna elements, and there are multiple ways to create an array in MFM. The most straightforward is to use array.create, and that will create an empty array object when no arguments are passed to the create function. So as you can see over here, we have an array object with no elements. If we want to create a uniform linear array of 8 elements, we can do that with just an argument of 8, and now you can see the array object has 8 elements, and by default it's created along the x-axis, so the y and z coordinates are 0. If we wanted to create it along the y-axis, for example, we could just pass an argument y, or of course z if we want it to be along the z-axis. So let's go ahead, and we can of course pass x even though it's by default. So let's go ahead and create a uniform linear array of 8 elements along the x-axis, and we can view that array using show 3D, for example. So this will open up a 3D plot window where we can see each of the elements. Again, it's along the x-axis, and we can see this in 3D, of course. By default, the array elements are centered at the origin, and it's half wavelength spaced. So if a user wants to create something other than, a uniform linear array or a uniform planar array, for example, they can do so by creating an empty array object and then adding the elements individually based on their coordinate. And all the coordinates of an array object are in wavelengths because the array behavior and characteristics depend only on the relative spacing, the spacing relative to the wavelengths, that is. So it does not need knowledge of the actual true coordinates other than their representation in wavelengths. So you can also view the array in 2D, which by default shows it in the XZ plane. So if we're not sure how to use a function, so right now, off the top of my head, I cannot remember exactly how to use the show 2D function, if it takes extra arguments or not, we can just type show array or help array dot show 2D, and you can see that there is inline documentation. So MATLAB will automatically return this inline documentation when you type help and that object's function. So you can see, in fact, we can pass an axis handle for it to plot on if we have one already, or we can specify the plane. So for example, by default, remember it plotted in the XZ. We can also specify XY and YZ, for example. So to do that, we would just do pass no axis handle, and then a string specifying which plane. So if we want to plot in the YZ plane, for example, we look at it, of course, in the YZ plane, it just looks like one element because we're looking along the x-axis, and that's the axis on which the array was built. So you can see there's quite a few options when using a lot of these functions, and if you're ever confused on how to use them or don't recall, you can always use the help command. Every single function has been documented so that its help is available in MATLAB. It's also available on the MFM website in case you get stuck. And there's extra guidance on the MFM website that may provide some clarifications. Okay, so let's get back to playing with the array object. So you can also create an array object as a uniform planar array, for example. So if we want it to be an 8x4 planar array, we can do that, and now you can see we have 8 rows, 4 columns, and that is our uniform planar array. Okay, so and we can also pass an argument as XY, XZ, or YZ to specify which plane to create the array in. So notice now the planar array was created in the XY plane, which is what we specified here. By default, it's created in the XZ plane. Okay, so there's our planar array, and if we want to view the array response as a function of angle, so the array pattern, we can show array pattern using that function. And if we run this, we get our window of 4 plots. So on the left side we have the azimuth cuts. So these are as a function of azimuth, and these on the right are as a function of elevation. So we have 8 elements in elevation, which is why we have a much narrower pattern here in the elevation plane, or in the elevation cut, and then we have a much wider pattern in azimuth because we only have 4 elements in the azimuth of our uniform planar array. Some other functions that the array object has, I'll go ahead and comment some of these out so they don't keep showing up, is the get array response. So if we want to get the array response, which is the vector of relative phase shifts across elements for some azimuth and elevation angles, we can use the get array response with 2 parameters. So the first argument is the azimuth angle. So if we're curious what the array response is at, pi over 3 in azimuth and pi over 6 in elevation, for example, we can get that just like that. So one line, MFM will automatically compute the array response as a function of these angles. If you don't specify an elevation, it will use a elevation angle of 0. So you can do, you can basically focus solely on the azimuth plane if you want, rather than working in a 3D view. But MFM does support 3D if needed. So that's the array response function. We can also use this array response function, for example, to beamform in a particular direction. So if we want that, let's go ahead and use a uniform linear array along the x-axis. If we want to beamform along pi over 6, for example, so that's 30 degrees, we can get the array response vector, which we'll just call r. And so if we do that, just to show you, we are working with a uniform linear array now of 8 elements along the x-axis, just for simplicity rather than working with a planar array, which is a little more complex. Okay, so we have our uniform linear array of 8 elements. We've gotten its array response in this vector r. And now, if we want to beamform toward pi over 6, it's as simple as setting the weights of the array to the conjugate of r. So we've done that. And now if we go and check out the array element, or the array object A, and we look at its weights, we can see that, in fact, it has been set to the conjugate of r. So by doing that now, if we plot the array pattern, we can now see that it's beamformed toward 30 degrees, and all of its gain, all 8 elements, are coherently combined to supply a gain of 8, a linear magnitude gain of 8, in the direction of 30 degrees. Okay, so this is just one way to beamform. Of course, you can create weights however you want. This is just conjugate beamforming, often called, or matched filter. But this is just one way to set the weights of the array. So we can also rotate and translate the array. So if we want to move the array, for example, let's go ahead and do that up here. We can rotate the array using just simply a.rotate and then specifying the rotations to make along each axis. So if we want to rotate it along the z-axis by pi/2, for example, we would do something like this, and instead of, let's do pi/2, and if we look at it in 3D, we can see now that the entire array was rotated. It looks a little weird here, almost caught me off guard because, MATLAB, there's these little residual non-zero terms, but we can just do axis equal to go ahead and view that again, and now you can see that in fact it is along the y-axis now. So that is the rotation function. We also have translation, so let's go ahead and do a.translate, for example, and this will translate or shift the array around. So this can be done by specifying the shift to make in the x, y, and z coordinates in wavelengths, remember. So this is, if we want to shift it by, let's say 8 wavelengths in the x direction and 0, and let's go ahead and shift it by 8 in the other also, just for the fun of it. And then let's view the array. Oh, I'm sorry. Now we can see that it's now centered at 888 because we've shifted it from the origin up to 888. Okay. So that's how you can move an array around and rotate it and physically manipulate the array. You can also get the array gain with a simple function. So array dot get array gain will return the array gain in a particular direction. So this is the weighted array gain. So if we want to get the array gain in the direction of pi/6 in azimuth and 0 in elevation, we can do that using that function. And the array gain in the direction of pi/6, since recall we've steered toward that direction, is in fact 8. So if we look at, we can try other directions, and of course it's going to be less, and it is the complex gain that it returns, so that's why this is a complex number. But you can see the magnitude of g is always going to be less than 8, except in the direction that we've steered. We can also get the polar array response, or polar array pattern rather. So we can do that using functions like this to get these nice, fancy-looking beamforming figures, which may be preferable than the typical Cartesian plots. But that's pretty much it. This is the array function. Typically, arrays in MIMO are just used. Beamforming isn't used in this fashion. A lot of times you're doing precoding or combining in the digital domain rather than sort of in this pseudo-analog fashion. But still, the array function and its beamforming capabilities can be useful for other applications beyond MIMO, for example, sonar and radar, things like that. And it can be used on its own, for array design, and you can obviously shift the elements as you need to. So if you want to implement noise on the array, or whether that be in the array elements positions or in their phase, a lot of these different things can be implemented using the array object in MFM. The array object is probably the most useful, in my opinion, object here in MFM, just because it's so low level. It can be used for so many different applications. It can be used on its own rather than with the rest of MFM. Anyway, this concludes this video. Please feel free to reach out and view the website for more information. Thank you.